So here boundary conditions for this. So the boundary conditions for the first order equation in YO are at the flame, from the flame outer region, from the flame to infinity. So at R equal to RF, Y equal to YO equal to 0. At R, as R tends to infinity, YO is the YO infinity, which is now taken as 1. Okay. So now again the property 1 by 4 pi rho d, which is already defined as ZF. I am keeping that same here, okay, because the rho d is constant here. So rho d for fuel or rho d for the oxidizer are the same. So it's only ZF. So that is already defined. So that variable is used here. So same type of solution I get, some same small change here. You can see this. Now applying the boundary condition YO equal to 0 at R equal to RF. So when I substitute here R equal to RF, I will get YO equal to 0. Constant can be evaluated. Well, other quantities are known to me. So once the constant evaluated and put back here, I get the profile for oxidizer. So that is YO of at any R equal to S times exponent of minus ZF m dot F by R divided by exponent of ZF m dot by RF minus 1. Okay. So this is the profile. Okay. So now you can verify this. So when you put YO equal to 0, you will get RF. Then actually if you put RF here, this and this will cancel and become 1, and 1 minus 1 is 0. So YO will become 0. Okay. So now one boundary condition is used here. Then I will use one more boundary condition in the profile, which is nothing but as R tends to infinity, YO tends to 1. If I use that condition, when I put R infinity here, so this will be 1 by infinity 0. So this is 1 by this minus 1, 1 by exponent of minus ZF m dot F by R of minus 1. That will be equal to, here it will be 1. So when I use this, okay, I get another equation which I call F. So this is another equation which will involve flame radius. Okay. Now please understand that it has two unknowns here, flame radius as well as this m dot F. So I get this. Okay. So maybe I can say that I will write flame radius in terms of m dot F. So everything I can write in terms of m dot F. So this is the second equation I have generated. The first equation what I have generated is this YFS in terms of m dot F. So that is equation E. Now I am writing RF in terms of n dot S, or other way, whatever you want you can keep. So there are two unknowns here again. So I have created a second equation. So two equations are created by considering the species conservation in inner and outer regions. Now I will do the energy conservation. Again I have energy conservation to be done in the inner and outer regions. That will generate two more equations, correct? So two equations are now generated. One is the equation due to the species conservation in the inner zone. Another one is that is fuel conservation. Second one is the oxidizer conservation in the outer zone. Then I have got this second equation. Now energy conservation. Please understand that there is a thin reacting zone. Okay, this is the inner zone, the outer zone. So thin reaction zone. So only at R equal to RF, infinitely fast reaction is complete. So that means just left side of this. Okay, so this is RF. So I will say RF. Just left side of this, I will say RF minus, and just right side of this, I will say RF plus. Just okay, in the thin zone, just to the right of that, I will say RF plus. Just to the left of that, I will say RF minus. You will see there will be no reaction because reaction is complete within the thin zone. So this is very important that infinitely fast reaction is occurring. Infinitely fast. That means when you just step out of the thin zone, you will not have any reaction. That means chemical reaction is assumed to be occurring only in the thin film sheet. This is correct. They are very fast. So other than R equal to RF, when R is not equal to RF, the reaction rate is taken as 0. Only at the location of R equal to RF, reaction is started and finished. 0 thickness, infinitely fast, so very very thin. Thickness of the reaction tends to 0 as the reaction rate tends to infinity. Okay. So in both outer and inner regions, you will see that reaction rate is 0. So the energy conservation is a simple second order equation which is written in this. So this is diffusion term and convective term. You can write that d by dr of r square and dt by dr will be equal to, actually this will be 4 pi, should come this side, and lambda 4 pi, here lambda also should come inside, but we have taken everything coming to the other side because we have treated CPG, lambda, MF etc. are constant. So, some constant time dt by dr. So, this is diffusion and convective terms are there. So, now please understand that this equation is second order equation in the involving temperature. So, that we can basically go and integrate. So, boundary conditions we have to appropriately use, but please understand that there are two regions, inner and outer region. So, the same boundary equation can be used to solve both. So, boundary condition for the second order differential equation in temperature. Okay, now there are two regions, as I told you. Inner region as at R equal to Rs, equilibrium surface temperature T equal to Ts prevails. At R equal to Rf, T is the maximum flame temperature Tf, and an outer zone starting from R equal to Rf, you have flame temperature 2, and as R tends to infinity, T will tend to T infinity. So, these are the boundary conditions at the both zones, inner and outer zones. Okay. Now, let us define the properties Cp by 4 pi lambda as Zt. Zt, that is the basically you can see that Cp by the properties where that 1 by 4 pi rho d etc. we have taken as Zf. Here we have taken the coefficients, the properties clubbed together we have taken as a constant Zt. Now, integrate this 2 times, second order equations you can integrate 2 times and I get 2 constant, one for each time. Then this is the profile I get, general profile, and in this if I apply the boundary conditions corresponding to any zone I will get the equations. So, let us take inner zone first. There are 2 constants. To eliminate the 2 constants I need 2 boundary conditions. So, taking inner zone, the boundary conditions what I am going to use are at R equal to Rs, T equal to Ts. So, when I say here I will put R equal to Rs, then T, say here R equal to Rs, I will say T equal to Ts, then I will form one equation involving C1 and C2 where the left hand side is Ts and right hand side R will be replaced by Rs, and so one equation in C1 C2. Second equation will be at R equal to Rf, T equal to Tf. And substitute here R equal to Rf, T I will put Tf. Okay. Now, please understand that Tf is not known, Rf is also not known, but I will form again equation corresponding to with the C1 and C2 where I will have variables like R1 or Rf and Tf or Ts, all the 3 are not known to me yet. So, now I get the equation. So, when I solve for C1 and C2 by these 2 boundary conditions in the inner regime, then I get the profile for temperature given here. It is a very big profile. So, you can see Ts minus Tf, okay, into exponent of minus Zt, which is the property constant Mf by R, plus Tf into exponent of minus Zt Mf by Rs minus Ts into exponent of Zt Mf by Rf. Okay. So, now please see that the temperature profile basically in the inner zone consists of Ts and Tf, because now for the surface the influence of the T ambient is gone, T infinity is gone. So, Tf and Ts, that is the driving force here. So, that we have seen here. Now, this is the equation I get, a big equation for the inner temperature profile, but please understand that the unknowns here again are Mf. Mf is not known, Ts is not known, Tf is not known, and Rf is not known. Only Rs is known here. So, anyway, we will try to use some boundary conditions, some more boundary conditions, and use this equation in order to get this. Basically, we are going to see the other boundary conditions also. We have to generate 5 equations. This itself has 4 unknowns. So, this is also a profile. Once the unknowns are known, then the profile can be plotted. That is the idea here. So, now same thing you do for the outer zone, the same profile, this equation is valid for the inner zone as well as outer zone, but the boundary conditions are different. Based upon the boundary conditions, the constants C1 and C2 are evaluated. So, by doing for the inner zone, by substituting the inner zone conditions R equal to Rs, T equal to Ts, R equal to Rf, T equal to Tf, we have evaluated this profile. Again, please understand that once all the variables or the 5 variables what we are talking about are known, then the profile can be drawn. Now, outer zone, again you have to use the boundary conditions of outer zone, that is at the flame, outer zone at the flame R equal to Rf, T equal to Tf, flame temperature. As R tends to infinity, T will tend to T infinity. So, these are the 2 boundary conditions to evaluate the two constants. The same profile you take, but now substitute R equal to RF in the right hand side, put T equal to TF here. So the same first equation what we get here for the inner zone, the second equation will be there as the first equation here. Then you go to the when R tends to infinity here, you put R infinity here, so this will be 1 by this, etc. Then you will get another equation in C1 and C2. So solving C1 and C2, I get the profile for the outer zone. As now you can see that the outer zone Tf and T infinity are the two temperatures involved. So Tf minus T infinity exponent of minus Zt mf by R plus T infinity times exponent of minus Zt mf by Rf minus Tf. So this is the equation. Now we can check the boundary conditions. You can go back here, you will check the boundary conditions here. So if you say R equal to Rs, so now this will be Ts. I put R equal to Rs here, so here Rs, and when you put Rs here, then Ts into exponent of minus Zt mf by Rs plus, so minus Tf plus Tf, that will cancel, Ts into exponent of this minus Ts into exponent of this will come, but Ts you can take common outside, and the exponent of Zt mf by Rs here, and minus of exponent of minus Zt mf by Rs this. So this will cancel and I will get T equal to Ts. So when you go to other condition where R equal to Rf, if you substitute here Tf will come and you are putting Rf here, then you can see that Ts this plus Ts into exponent of Zt mf by Rf and minus Ts exponent of Zt minus Zt mf by Rf will cancel. Then here you can get Tf, you take commonly out, and Tf times exponent of Zs mf by Rs minus Zt mf by Rf. So this will cancel and we will get T equal to Tf. So the boundary conditions, the profile is matching the boundary conditions basically. Similarly here you get the outer zone. Outer zone you have flame, R equal to Rf, Tf is the temperature here, and as you go to infinity you get T infinity. Okay. So now you can substitute here and see, if you put say T as R goes to infinity, basically you can put this will be infinity, so this will be 1. So Tf minus T infinity plus T infinity into, so Tf cancels basically, T infinity into exponent of this divided by this. So T infinity into 1 minus this will come. So if this minus 1 will come, so you can this exponent terms will cancel, exponent term minus 1 will cancel and get T infinity. So if you get if you substitute R equal to Rf here in this R equal to Rf, you will get Tf in the left hand side. You can see whether you get it, you will get it. So the main crux here is, now we have developed the profiles, but the profiles cannot be plotted because I don't know. Here also you can see the unknowns are mf dot, Tf and Rf. These are the three unknowns present here. So since after evaluating all the unknowns, we will be able to plot the profiles. But how will you generate the equations? These cannot be used now. So already we have created two equations, one for the say for example one relating the YFS and MF, another relating the RF and MF. Okay, so we have created two equations. See here, one equation is the RF and MF are related, and here I have related YFS and MF. Okay, now three more equations are required. So now we have generated profiles for inner and outer zones for temperature. Now is there any way to use this profiles to get the conditions, two more equations? Okay, for that I will first do the energy balance at the interface. Okay, so interface. So what is the energy balance here? As we have drawn it already. So that will be Q, okay, gas to interface. Q gas to interface, and that will be taken inside here. So Q interface to liquid, and vaporization occurs. So m dot H F m dot H G. Okay. Now dividing by the mass. Okay, this small QL is nothing but Q I to L by m dot. Okay. So that you can so this m dot f into this, so m dot, you can say m dot f actually here, fuel is actually generated out, so m dot f. So when I do this q I to L, q dot I to L by m f dot, that will give you the heat which is going in, okay, going in the interface to the liquid phase, and this is the heat which is required for this HFG, Hg minus Hf into m dot f, that will be the heat which is required for phase change. So that is coming in through the conduction from the gas phase to the interface, which is written as this. This is the q dot I L divided by m dot f. So this is the term, okay. So now this is the interface boundary condition, heat balance at the interface, okay. See, we have taken the boundary conditions, the additional boundary condition I am trying to create here, where derivative of temperature is present, and since it is done in interface, I can calculate this dt by dr, okay, dt by dr of the above equation can be evaluated using temperature profile for the inner region, that is this. So this equation I will take, differentiate it with respect to r, so I will get dt by dr. Once I get this value, I can substitute here and set, okay, this dt by dr evaporated using temperature profile in the inner region, and r value is set to rs, okay, because I want the derivative at s, at the surface. So you take this profile, inner profile, differentiate this with respect to r, so dt by dr, then there will be r terms, that r you set as r s. So that will give you this equation. Substitute back here and try to get an equation. That is what we are trying to do. So this is the equation which is representative of the heat balance at the interface. So this is the equation. You can see the unknowns are m dot f, Tf, Ts, r s. So r is not r is rf, rf here. So these are the unknowns in this, okay. These are the unknowns in this: flame temperature, surface temperature, RF and m dot f. So this is the third equation we have generated. So already two equations, one for the inner region species conservation, fuel conservation, outer region oxygen conservation, by using the balances, okay. We are trying to get, now here after getting temperature profiles, we are trying to put the heat balance at the interface. Based upon that, I get this equation. So this is the third equation I have generated. Now let us do the heat balance at the flame sheet. Next is the heat, energy balance or heat balance at the flame sheet. This is flame, okay. Now how the heat balance occurs here? So whatever be the chemical energy converted into thermal energy, okay. So this is here. So whatever be the chemical energy which is released out as thermal energy, that will partially be transferred. So this is the flame, so this is surface, so this is RS. So partially it will go here, like that is from the flame, this is the Q dot flame to interface. So partially it will go towards interface to heat up the, or to supply the heat for the droplet, and partially it will go away. This is Q flame to ambient. It will be lost away, so it will go away. So this is the thing. So this should balance what? The chemical energy release, which is nothing but delta Hc, correct. So this is m dot f into this. So this can be the enthalpies, if you properly write, you can consider for example enthalpy to be constituted as the formation enthalpy plus the sensible enthalpy. Sensible enthalpy is, we have constant property, so T minus some reference temperature we take Tf. So this will be the this. So this actually, no, the temperature actually is Tf also you can write, because Tf is the flame temperature. So the enthalpy of any species. So now I have taken an example of fuel. Enthalpy of fuel will be the heat of formation of fuel, Hf of f plus the sensible enthalpy, which is nothing but Cpg into T minus Tref, but T is actually the flame temperature itself. So Tf minus Tref. So this will be the enthalpy of this. Similarly, you can write for the enthalpy of other species. See, for example, oxidizer, this enthalpy formation may be 0, but only sensible enthalpy may be prevailing. but please understand that CPG is constant for all. So, for all these terms, sensible enthalpy can be written as Tf minus T reference into CPG. So, that is what we will have for all the species as a sensible enthalpy. Formation enthalpy based upon whether it is fuel or oxidizer, we will have some values. Now, you can see that delta Hc is the heat of combustion, which is nothing but the enthalpy formation of the fuel plus enthalpy of formation of the oxidizer, which can be 0 actually, into S minus 1 plus S of enthalpy of formation of products. So, this will be normally 0. So, this is the expression for the delta Hc. So, using these in this, so this enthalpy definition etc., and definition of delta Hc, we can write this equation basically. But one more assumption what is made here with respect to the CPG into Tf minus Tref is, if we know that CPG is constant. Since CPG is constant, basically what happens is delta Hc will not be affected by Tf. So, Tf itself can be taken as the reference state basically. So, Tf, if we take Tf as reference state, then the sensible part can be neglected. Okay, reference temperature also, this is Tref, correct. Now, Tref is also taken as Tf itself. So, this term sensible enthalpy goes away. So, we will only consider this. So, now what happens in this case, I can write the left hand side as m dot into delta Hc, that is, I can see that m dot into delta Hc is nothing but the thermal energy generated at the flame zone due to the chemical reaction, that is all. The mass of the fuel which is coming out of the from the liquid surface, that is fully burnt. So, that times delta Hc, okay, that will give you the thermal energy which is generated. So, that should be partially conducted back to the inner zone, that is Rf minus represents the inner zone. So, conducted back to the inner zone and transported to the outer zone. So, this is the conduction to the outer zone, Rf plus. So, this is the equation what we get. Now, you please see here the Qgi gas to the interface. If you say the interface, this is the so actually this is actually gas, you can also say flame, both are same, either from gas phase to the interface, but here this is actually flame, okay. Flame to this, we have written here flame, flame to the interface and flame to the infinity. So, from the flame, this is a flame sheet. So, you can see that this conduction, when I write this G2I here like this will be negative of minus 4 pi Rf square lambda into T by dr. Okay. So, that is going out like this to the inner zone. So, minus of minus why I am putting, because this is the direction from Tf, temperature decreases towards the Ts. So, this gradient is negative. So, there is a positive, the heat flow also is in this direction. So, that is positive, but this negative sign is put because this flow happens, it is a vector and happens in the negative radial direction. So, negative radial direction, correct. So, this is the negative radial direction. So, this negative I put, so this is a positive quantity here. Okay. Now, if you take this side, okay, here you have 4 pi Rf square, that is the area of cross section, into lambda into dt by dr. Okay. Now, at Rf means this is the, so again you can see that from this point I will put a negative sign here and leave it. Okay. Negative sign and leave it. Why I put negative sign here? Because we know that the temperature gradient is negative, temperature decreases there, correct. So, temperature upstream minus the temperature downstream minus upstream will be actually negative. So, this is negative and the heat flows in this direction, basically this is the negative term. So, this negative term comes because of this term here, because this has become positive, negative, positive because of the direction of the heat. So, these are vector forms. So, these are vectors basically. So, the heat flow, any flow or flux, when you have a direction, you have to take care of the signs. So, the negative comes because of the negative radial direction. Here in this, the heat flow and the radial direction are in the same direction, positive radial direction on the same direction. So, this negative sign is to take care of the gradient being negative. So, the chemical heat converted into thermal energy will be equal to this, partially used to heat the interface or supply the radiant heat, partially transported away to the ambient. So, this is very important equation. Now, please understand that this equation now gives the energy balance of the flame sheet. Now, I have two derivatives here, temperature at the RF minus, that means I have to get that temperature gradient at RF, I have to take the inner profile, and here RF plus I have to take the outer profile. Okay. So, now the dt dr terms here, dt by dr terms here are evaluated using the temperature profiles in both inner and outer regions first. Okay. So, for this value dt by dr at RF minus, I will take the inner temperature profile. This inner temperature profile I will take, calculate the dt by dr and set R equal to RF and use this here, because at RF, no. So, set R equal to RF and use this here. In the other one, this derivative I will take from the outer zone here, the outer zone, this profile I will like a differentiation of this with respect to the radius and set R equal to RF. So, I will get the values here. So, when I do this, I get the fourth equation. Sorry. So, first equation was due to the species transport in the inner zone, that is fuel transport in inner zone. Second equation was generated using the oxygen transport in the outer zone. Third equation is generated using the interface heat balance using the energy conservation. Inner temperature profile was used, and inner temperature profile using that derivative term calculating differentiation of that temperature profile with respect to R and setting R equal to RS, I got the heat balance at the interface. That was the third equation. Fourth equation is the heat transfer at the energy heat balance at the flame sheet. So, there we get two temperature derivatives, one for the inner zone, one for the outer zone, and use that and get an equation. So, there are now 4 equations, but 5 unknowns are there still. So, the 4 again, please see that this equation has m dot f, Ts, Tf, Rf as the unknowns. Basically, there are 4 unknowns here. Okay. So, what is the next step? Where the 5 equations are there, so how the 5th equation can be created? There are 4 equations I have used. So, now please understand, conservation equations for species, see there are 2 species, so only one conservation equation can be used. The other one can be found as 1 minus the mass fraction of the other species. So, one conservation equation is enough for one inner zone and outer zone. For the inner zone we have used fuel, for the outer zone we have used oxidizer. So, now you got 2 equations out of that. So, now temperature we have 2 profiles for inner and outer, and we have the balance, heat balance at the interface providing one, heat balance at the flame sheet providing one more. So, we have consumed all the boundary conditions now. So, 4 equations are got. 5th equation is not available, there are 5 unknowns here. For getting that, I need to connect this Ts and YFS. That means the 5th equation can be generated using the thermodynamic relationship, this Clashes-Clapeyron equation. Okay. So, these are the important things. Now, go to that. So, Clashes-Clapeyron equation as we have seen already, which is written in a different form. Okay. When I saw this droplet evaporation problem, here this is the Clashes-Clapeyron equation. So, XFS equal to P saturation by P equal to exponent of this. So, but you can see this, these are the variables which are known to us. T surface, if you substitute, I get the XFS value, but the fuel properties like HFG and T boil has to be given as an input. So, now this equation itself can be written as, so this equation itself can be written here